Till now, we have seen the optimization equation for logistic regression is to find a W, that's the weight vector, which minimizes this expression. So, sorry. So, and we also learned that this represents the loss for the logistic regression. Now, the minimum value for this expression, if you can see, is will be attained. That we know log 1 is 0, and obviously the minimum value would attain if this tends to 0 when exp of minus yi w transpose xi tends to 0. And we know the values yi and xi are constant, so only w transpose xi can make this tend to 0, which implies, and this happens only when w tends to infinity. So when w tends to infinity, the minimum value for this expression can be attained. And also, whatever may be the case, this value will always be greater than or equals to 0. But, sorry. So, when w tends to infinity, we get a minimum value of 0. And this actually, like, if you can think a weight vector going to an infinite value, it's not proper. And this results in overfitting issue, because what it's trying to do achieve is it's trying to find a value w which can classify all the data points correctly, and that can happen only when this value tends to infinity, which is very high value. So sorry. So to overcome this issue, when where w tends to infinity, or when w tends to minus infinity, uh, what we have to do is introduce a new expression such a way that uh, w doesn't tend to infinity, the minimum, to attain the minimum value of that expression. So that is called as regularization. Regularization. What it states is, still we will be finding a w which minimizes summation of I equals to 1 to n log 1 plus exp of minus yi w transpose xi plus lambda times w transpose w. So what essentially it's happening is, say if we had only this expression, the first part of the expression, and when w tends to infinity, then this whole expression would become 0. So what essentially happens is, uh, the minimum value of this expression will be attained. And as we discussed earlier, it would cause an overfitting issue. So to handle that, we are introducing a new term here called as regularization. So what it makes sure is, when w tends to infinity, even though this tends to 0, but this value would tend to infinity. So this condition will not be attained, like the minimum value of w means the w for which a minimum value for this expression will not be attained for both the cases, when w tends to infinity and w tends to minus infinity. Yeah. So like using this regularization term, overfitting issue is eradicated. So, and this is called as an L2 norm. And this can be rewritten as lambda times of L2 norm. And here lambda is the hyperparameter. Lambda is hyperparameter. Now, how can you find the value of lambda? So to do that, we can use the same techniques that we used in KNN, K nearest neighbors. So we would be plotting the cross-validation error with different values of lambda, and this value can be um, found using two techniques, either grid search or random search of lambda. And while doing grid search, lambda value will be uh, found, or else for different values of lambda, cross validation error is found, and those values would be between 10 power minus 4 to 10 power 4 for this range of values. And it's not that for each and every value a range means it, it's a different range is defined as 10 power minus 4, 10 power minus 3, 10 power minus 2, uh, 1, 10, 10 square, 10 cube, and 10 4. So for these values, a plot between cross validation error and lambda is plotted. And as we have seen in K nearest neighbors, we would like kind of getting this shape, and where the error is lowest, that lambda is identified.